Let's talk about nickel metal hydride cells, how to charge them, and the problem with smart chargers. So I've got a selection of cells here, not all of which are nickel metal hydride, but I'm going to put some cells in. I'm going to put in this cell that is probably going to not charge up to a very high capacity. It's been recognised. I'm going to put in an old nickel cadmium cell, which has not been recognised, and we'll see if it is recognised later on. And that has also not been recognised, and I'll explain in a moment why that is. So I'm going to take this one out because I want to actually demonstrate. I want to see if that one does actually in any way take a charge. But that is now charging at 200 milliamps, and if I click this button, it will show how many milliamp hours it's put in, and more importantly, it will show the voltage across the cell. Right, so let's talk about nickel cadmium first, and because nickel cadmium was the precursor to nickel metal hydride, and nickel cadmium goes back a long way. But when the European directive came in for getting rid of things like reduction of hazardous substances and things like that, they didn't want the cadmium in landfill, so they chose to switch to nickel metal hydride cells. And in a way that was good because there were many advantages. For a start, a nickel metal hydride cell, even a sort of cheapy one like this, has relatively good capacity compared to the old nickel cadmium ones. The nickel cadmium ones were also very prone to self-discharge at a fairly high rate. MD who used the old nickel cadmium power tools, like the Ryobi battery pack, will know just how rapidly they'd self-discharge. It was extremely annoying. You fully charge it up, you go back later on, it's discharged. That lithium has blown everything out the water. But the advantages of nickel cadmium over the nickel metal hydride were that it's a very robust battery technology. It's really rugged, has a very long life, and it will operate at extremely low temperatures, down to about minus 20 degrees Celsius. So nickel cadmium, still like this yellow cell here, it still has its place. And it's used in medical applications and also emergency lights where it's just left on continuous trickle charge all the time. And it's one of the most robust technologies for that. Next comparison is between nickel metal hydride, like this premium Eneloop cell, and lithium cells. It's very hard to compete with lithium, but if you were to put these in your pocket and you were to short these out, the nickel metal hydride would potentially get very hot if it's shorted with keys, but not as hot as the lithium cells. If you short lithium cells out, unfortunately, it can go into thermal runaway. It's not the lithium that's blowing up, it's just the fact they contain so much energy and it all comes out at once that it causes problems. Particularly, that's why a lot of the manufacturers distanced themselves from the 18650s. They said they're not suitable for personal use. They should only be built into equipment. And in a way, they're right. If people stick these in their pockets, that's when you see people's pockets going on fire. The whole point of that thing, of the manufacturers putting that out, was to basically say, we're not liable because we told you so. But moving on from that, if I had to choose a technology, it would be LiFePO4, lithium iron phosphate. It's got lower energy density than traditional lithium ion cells. Well, it is lithium ion, but the ones we normally use, the ones that charge to 4.2 volt, this charges to a lower voltage. But although it's got lower energy density, it's much safer. Its electrolyte isn't flammable. That's one of the problems with these. It's the flammable electrolyte vaporizing, igniting. They tend to fail with a sizzle and let the fumes out, but not too badly. But also they're super robust. If you put these in storage, this one, the lithium iron phosphate, would be more stable in storage. This would lose its energy density over time. This would keep its energy density, and this one's going to charge for a lot more cycles. I wish there were more lithium. I want my phone to have a lithium iron phosphate battery, but I think its high life is probably why they don't put them in phones. Because they want you to buy a new phone every year. Oh, that was a bit conspiracy theorist. But anyway, what's happening here? This one is taking a charge. This is good, actually. It's doing better than it did before when it put a grand total of 1 milliamp hour in and then decided it was fully charged. I shall come back to that in a moment. I'm going to bring the notepad in and I'm going to talk about how to charge these cells. So the simplest possible circuit for charging a nickel metal hydride cell is, say for instance, plus 5 volts. A nice handy voltage from your USB power supply, a diode, optional, just to stop it back feeding to the supply when you unplug it, a resistor to limit the current, and the cell. And that is it. 0 volts. That's all you need to charge the cells. And you think, well, what happens if you overcharge it? Well, you can't. If you keep charging a nickel metal hydride cell like this, as long as you don't do it to a ridiculous level, as long as you don't smash amps through it, it can do something very clever. If I, say, draw the outline of a cell, like this, so there's the cell, there's the pip in the end, here's electrode materials inside. When it gets to the end of charge, bubbles form on the electrodes. It liberates gas. Most cells do that. And when that happens with nickel metal hydride or NiCad, it does what's called self-catalysis. As long as the current's not too high, it can convert this gas back into liquid electrolyte. And in doing so, the temperature rises a little bit. In the case of the old nickel cadmium reliably batteries, what they used to do was they had a thermal switch in them. They had a group of cells, and in that group of cells, they had a little thermal switch sandwiched down the middle, and at the end of charge, the way it detected the pack was charged was the thermal switch would cut out, and it would either break the current or just break a control signal to the actual controller, charge controller, and it would turn it off. Very straightforward. This compares very favourably in a way, but it's pros and cons to lithium cells where you cannot trickle charge a lithium cell. If you keep trickle charging that, the voltage will go above 4.2 volts in the standard lithium ion cell, and it will potentially go unstable. It will damage it. At the very least, it will damage it. At worst case, it may initiate failure of the cell. Let's talk about the discharge curve of nickel metal hydride, which also makes it fairly useful, makes it a bit annoying when you're trying to replace alkalines with it. If this is, say, 1.5 volt, 1.5, and this is 1.2, and this is 0 volt, it starts off at a full charge round about 1.5 and rapidly goes down to 1.2, but then hogs 1.2 all the way to the end, then suddenly dies off at the end. And again, if in the days of the early, especially like nickel cadmium power tools, you'd be drilling a hole and suddenly you'd hear the motor go, and it would just suddenly go down to a lower speed because one of the cells had just reached the end and it just fell off a cliff, and it just basically, the voltage just dropped. That constant voltage is another nuisance. This is where lithium wins again, because the lithium, if you measure the voltage across a lithium cell, it will give you an indication of the charge state that's in it. If it's round about 3 volts, it's pretty flat. If it's 4.2 volts, it's fully charged. If it's 3.6 or 7, it's got about half the charge in it. It's a really handy way of doing that. Also, when you put this into a charger, it will charge it from any level, whether it was almost full or almost empty. It will charge it up to exactly 4.2 volts, and then it will stop, and you'll know exactly that this cell is fully charged. That does not happen with nickel metal hydride cells. That is one of the problems of these smart chargers. So that is the trickle charger. But if you want to charge at higher currents, because typically speaking, to allow self-catalysis to take place, it has to be below 0.1 C. What that means is if the charge capacity of a cell, say for instance, this one is about, let's say it's 800 milliamp hour, you have to keep the charge current to about 80 milliamp hour. It has to be a tenth of the capacity of the cell typically to actually allow that process to continue. If you overcharge them continually in a trickle charging circuit, the pressure will build up and then it will vent gas out the end. The pressure build-up is an interesting thing because there was a battery technology, it's not available anymore. It's a shame it was the ultimate nickel metal hydride cell. It's a shame they discontinued them. That was Rayovac. But let's talk about the way this type of charger will charge the cells. Now at this point in time, this cell is taking a charge. It's currently at about 29 milliamp hour. This one is not taking a charge, and this one, when I put it in also, didn't want to take a charge. Let me show you why, and how to actually recover these to actually make them charge. Quite safely, it's normal. If you have 3 cells in series in a battery pack, it's worth mentioning. One of these is a cell, 2 of them in series is a battery. That's where the whole cell battery thing comes from. But you have these cells wired in series, and you have them powering a load like a lamp. And I'll show you this with a conventional current flow. I should zoom down this, shouldn't I? I should. So using conventional current flow from positive to negative, the current's flowing round and the current is sort of equal through all the cells. The middle cell goes flat first. They never have identical capacities, so one cell's always going to go down. That's the point in your power tool that used to be that suddenly the speed would drop as one of the cells went flat. What happens then is the current still keeps flowing. It's pushed around by the other two cells, but now it's pushing, making this side of the cell positive and this side negative, and it can actually damage the cells if you actually reverse charge them like that. That's what's happened here. These cells are either very flat or they've been reverse charged. When you put them into the charger, it can't see them because it's looking for a voltage to actually get an indication that the cell is in there. If that happens, this applies to nickel cadmium or nickel metal hydride. Take a power supply or bridge a good battery to a bad one. It's a very rough way of doing it. Or use a dumb charger. This is a trickle charger that charges at 100 milliamps continually. And if you put them in something like this, it will not only recover them, it will actually charge cells like this fully. Just take a lot longer to do it. But you can put a charge onto this to bring the voltage back up to the correct level. And once it's got a voltage on it, the charger, the smart charger, will detect that voltage and it will start charging. Let's recover this in the same way. This makes me wonder how many people put their cells into the smart charger. It doesn't charge them, so they just say, oh, that cell's dead, and they put it in the bin. That is not true. It's detected this cell as well and will now have a go at charging it. Let's talk about the fast chargers and charging at much higher currents above the point at which self-catalysis can occur and it can recombine the gas. So let's take a look at the options here. You have negative delta V. Negative delta V sounds very stylish. What happens at the end of charge with negative delta V is the charger puts the charge voltage across it and then takes it away and just measures the voltage. And it's looking for the point at which, at the end of charge, little bubbles occur on those electrodes, and for a slight load across it, the voltage will suddenly drop at the end of charge. And that's how it detects it. Now, it used to be quite a vivid drop with nickel cadmium. It's a very small drop with nickel metal hydride, and as such, many of these chargers can miss that. And if you put a battery into charge, this is just reported, these two, as being full when they're not. I'll show you why that is. It's trickle charged them, but it put almost nothing into them, and I'll show you why that is. So the negative delta V, it looks for that change in voltage, and it's very easy to miss it. So the other system it uses is no change of voltage. No change of voltage means it measures the voltage across the cell, and if it detects that the voltage just isn't rising anymore, it's static, it ends the charge at that point. The other thing it can use is delta T, which is my preferred way of, ultimately the change in pressure one is better, as I'll tell you in a moment. What's that called? IC3. But the delta T is temperature change. This unit does actually monitor temperature, I think. Some of them have a little thermistor actually soldered onto the end of each of the electrodes. And they can actually detect a sudden rise in temperature, because when it reaches the end of charge and the self-catalysis is occurring, it can't take anymore, the pressure builds up, but also because that chemical process is taking place, it warms the battery very slightly. In a low current trickle charger, it's not going to be much, it's not going to be even detectable. But when you're charging at 500 milliamps or an amp or whatever, the rise in temperature is vivid, so it goes from being a fairly ambient temperature, it will suddenly rise up, and it will detect that as the end of charge. Some also have a last resort. They will just say, if it's not charged in a certain time, it will just turn it off. But if you feel batteries and they're getting very hot in the charger, that means they're charged, usually. They should basically, you should stop charging at that point. It's the curse that smart chargers sometimes do weird stuff. One of those things, the negative delta V, and also the fact that they are looking for upper voltage threshold. It's designed to stop people putting things like alkaline cells in these. If you put an alkaline cell in, the voltage will go from the sort of, say, 1.2. It will very rapidly rise up to the sort of 1.5, and that's the point it rejects that cell. In the case of these cells, because it's got a high impedance and because it charges at the high current spikes, it will often reject low capacity cells. You know, things like the classic Kodak dollar store pound shop cell or this Daewoo one will often not take a proper charge in these, even at the low current setting. If that's the case, then put them in a charger like this and it absolutely guarantees to charge the cells up to their full capacity. That one originally only took a charge of about 1 milliamp hour. It's up to 49 now. Let's see what the voltage is. 1.4 volt. It's doing all right. It's recovering well. But when I put it in here and gave it a charge for a couple of hours, it actually took about 300 milliamp hour charge. So it must have been a good few hours I had it in this then. So the cell was good. It's just that this unit was not really recognising it. Its internal resistance was too high for this to put a charge into it. There is another curse with these smart chargers. One I got from Maplin with high capacity cells, and I put them into charge, went out the room, forgot about it, came back later. There was a strange smell. The Maplin charger was a very smart computerised charger, and it had crashed. It had crashed putting full current out to those cells. And when I was looking around the room looking for where the smell was coming from, checked all electronic items, saw the cells, all the heat shrink on them was basically just ripping and peeling back and shriveling. It actually glued itself. It stuck, it melted onto the back of the charger, which is a bit scary. And I immediately turned it off, and the cells, tried taking the cells out, but they were very hot, so I just left them in place, and I put it into a metal container just in case anything went really wrong with the cells, because they were so hot. But afterwards, when I turned it off and on, after I got the cells out, it's because it's computerized, it said, everything's fine, ready to charge cells. But as soon as that's happened, you kind of lose confidence. That's something you have to keep in mind with smart charging systems. Sometimes they're too smart. So these ones that have not taken a charge, these ones, if I put them into this cheapie, I think this came from Poundland again. If I put them into this cheap charger, it would be guaranteed to put a charge into them. And likewise, the trickle charger, it might take a long time to put a charge in, but it will charge whatever cells you put in up to their full capacity. Another thing I've come across with these, even putting good cells in, sometimes randomly, it will just terminate the charge prematurely. You get 3 identical cells that have been used in identical applications, and they've got basically the same capacity. 2 of them charge up to, say, they take another 1000 milliamp hour because they weren't fully discharged. The other one will only take 100 milliamp hour. And the reason for that is that it's done a false recognition of an end of charge state. It could be a bad battery contact. It could just be the chemistry creating noise inside. But sometimes it just messes up. I'd hoped this one was going to actually fail the battery. It's not. It's going to put a charge into it this time. But that, I think that sums most of it up. Nickel metal hydride still has a place. It has a place for devices that have the standard battery holders, although that helps if the equipment can actually recognise 1.2 volts. But ultimately, I have a horrible feeling that lithium is going to win overall. But until then, the good quality Eneloops and things like that, especially with their super low self-discharge, are definitely still a viable option. But if you've got a smart charger, just remember that sometimes they're not so smart. And just because it's not charging a cell might just mean that it's just needing that cell needs boosted in a dumb charger with something else just to put a voltage onto it. Don't just think the cell's failed because it may just not recognise the cells in place. But that is it. Nickel metal hydride cells. Quite interesting technology. Oh darn, bonus extra footage, because I forgot one of the most important breakthroughs that just never ever carried on. And it was Rayovac IC3 in-cell charge control. Let me draw a rough doodle of what I think was going on here. The in-cell charge control was the ultimate way of charging a nickel metal hydride cell. It guaranteed it was going to be charged right up to the end, to full capacity. It was never going to be overcharged, and it could be charged in 15 minutes. Even a 2000 milliamp hour cell could be charged literally with amps without overcharging it. Here's how it worked. There was an extra metal ring around the side of the positive pip, and when you put it into the charger, a metal cup made connection with that outer ring, plus a little stud in the middle meant it could charge ordinary cells as well. The middle stud just basically put in a trickle charge as such, so it would just gradually fill the cells up slowly. The outer one put the high current in. The high current bridged onto the middle stud, but when the end of charge was reached and these little bubbles started forming on the electrodes and the pressure built up, as soon as that happened, and I'm guessing this is how they did it, a pressure switch inside basically disconnected the outer ring from the center stud, and that ended the charge process, which meant that, if you put the battery in that was already fully charged, it would start charging at super high current, but the bubbles would form instantly and cut off. If the cell was completely empty, 15 minutes later, it would have charged it fully till those bubbles formed and it would cut off, but you couldn't overcharge it because the pressure inside was what actually determined the end of charge, and it meant that it was the perfect charger. So that was the Rayovac IC3 Rayovac. Unfortunately, I don't know why it didn't continue. Maybe it's because they were more expensive to make, too specialist, but it didn't continue. They discontinued it. Well, such a shame, because technically speaking, it was the perfect nickel metal hydride cell.